Okay, welcome to the lab. We're going to look at electron velocity and mass using a cathode ray tube. You'll soon see what the tube actually looks like. And this lab actually involves working with very high voltage, and which is good and bad at the same time, because it's bad because sometimes we're dealing with high voltages, which can be risky. But on the other hand, it's a pity that you are not here and not working directly with such voltages. So what we have is, if you look at the bottom, it's schematics of a cathode ray tube. Our old televisions and your computer monitors used to work with that. And if you look at the very back of it, it's not actually shown here. There are metallic filaments through which you pass AC current and make them hot. And when you make them hot, the electrons will come out of it. And then you actually pass these electrons through a series of what you call it potential differences. So when you have the potential difference, you have if you look at this, it says accelerator anodes. So the electrons will be attracted to those anodes and will pass through it. And there we actually apply very high voltage, 500 volts or 600 volts, and accelerate the electrons. And if you look at the very top line, electrons are accelerated to velocity Vx by a horizontal accelerating voltage V1. And when it gets accelerated, it actually assumes energy, of course. And if you look at, this is the kinetic energy it gets, half mv square. X is, we're only considering this x axis like that. And then it's the energy is actually the electron charge, which is E 1.6 times 10 to the power minus 19 coulomb, multiplied by the voltage difference that we are applying here. So, and that actually, if we know the voltage difference, we multiply by the electron charge. And if we know the mass of the electron, you can actually figure out what the velocity of the electron would be. It would be quite high velocity, actually. And then once it comes through, we can actually apply voltage either on the Y plates or on the X plates. And depending on, let's say, if you apply voltage on the Y plate, that's all we're going to do. So you actually can move this beam of electron onto the screen. If you don't put any charge, any voltage at all, let's say Y plate, the electron beam will go straight through and hit the screen. And there is some phosphorescent material inside of the glass on the screen. And when the electron hits this phosphorescent material, it will shine in green, actually. You'll get a green spot right here. And then when you apply voltage here, it's about 60, 70 volts. You can actually move it around. So we're only using electric field in this experiment. So you cannot actually determine the electron mass from this experiment actually by itself. And actually speaking, we will do another experiment later on with magnetic field. Even then, you're only going to get the charge to mass ratio, E over m, and not the electric field, not the electric charge and the mass separately. Because you need another experiment, which is called Millikan's oil drop experiment, to measure the electric charge, and then do this experiment with magnetic field to find the electron mass. So, it was a long haul to find electric charge and electric mass, and those experiments were awarded with Nobel Prizes. So let me go back to equation number 2. So what happens now is we apply a vertical voltage V2 to displace the electrons from central position. And when you apply that, the force is given by the electron charge by the electric field. And you say, how do I know the electric field? Well, if I know the distance between the plates, and I know I have applied 60 or 70 volts, which will be given, or you applied that voltage, you divide by the distance and you get the electric field. And this force will be equal to, with Newton's second law, F equals ma, mass of the electron times the acceleration in the y direction. Okay, so we had, this is number 2, and then I can measure this delta y with a ruler. Delta y is half ay t square. Okay, so look at all these equations. You have ay and then half ay t square. The problem is you have number of unknowns over here. Let's say I know what the mass is, because I cannot actually find the mass separately from this experiment. So if I plug this in here, and then I can get ay from that equation. Okay, and then from ay, if I plug that in here, I get the t square. And this is one of the objective of this experiment, to find this t. You will find that t is very, very small. The horizontal distance covered by the electrons are given by delta x is Vx times t. So in principle, I can, if I know the mass, if I plug it in here, I can in principle find the horizontal distance delta x. Or other way, if I know delta x, I can find Vx from here, and I can compare these two Vx's. Let me go down further. What we want to actually find out. So in principle, we're kind of going in circle, even though we kind of assume that you kind of know electron mass first, but then doing this, you actually find the electron mass again, which is really a tautology. So what I'm trying to say is, if you can find t from equation 4, and then you go back and actually want to find electron mass here, which is as if like you derive what your Vx is from here. If I give you delta x, you derive Vx from here, and go back and plug that in there to get the electron mass. The problem with here is that we have used, to find ay, we have used the electron mass here. So going back and plugging that back there doesn't really help that much. So in this experiment, what I want you to do, in principle, you find out Vx over here, okay, and then you find the time here, and see whether that time and this acceleration matches with our conception. The acceleration will be really very high, 10 to the power 15 meter per second square. And you say that acceleration, if the electron only goes for 1 second, it will go much, much faster than speed of light. But of course, that's not true. So what happens that the time it exists in this thing is only for a nanosecond or so. So by the time the electron is emitted from here, and when it hits the screen, it's only within the nanosecond. And that's the part you're going to find out from this experiment. So let me go through the procedure very quickly, and then we'll come back and do the experiment. We're going to connect all the bias voltages. We're going to connect the accelerating voltage. You'll see I'm going to do this for you. And then this is the part where we have x or y axis bias. That means that I'm going to have bias voltage applied here, so that the electron can go up and down. And then we're going to have this accelerating voltage until I see an electron spot on the screen, focus the spot, and then I'm going to deflect the spot by about 2 centimeters. And basically, that's about it, except for the fact that I would need to give you a couple of things. I will just give you this delta x, and I will give you also, I need to give you, otherwise it won't work, I'll give you this d, this distance right over there. And from those, you're going to find out ay and the time. That's basically our goal for this experiment, actually. So let me go over now to the experiment itself. It will not take much time. It's a setup which takes time. So if you're in the lab, this is the part you would have learned how to actually connect all the electrodes to the proper voltages, and then actually then focus the spot. We are going to do another experiment later on when we start with the magnetic field, and I will just give you a heads up on that. with these bias voltages, I'm going to move this spot with electric field, but then I'm going to put it in a magnetic field, and I'm going to bring that spot back with the magnetic force. And you're going to equate that electric field force with a magnetic field force. And in principle, again, we're going to go one step beyond what we have done here. We're going to get a ratio of electric charge over the mass of the electron, E/m experiment, famous Thomson experiment, a Nobel Prize winning experiment actually. And that's what we're going to do once we start the magnetic field chapters in our class, in our lectures. So I'll stop right here and I'll go over to the experiment part. Thank you. All right, now welcome to this portion of the lab. We have a cathode ray tube over here. I'm going to show you later on how it looks like from the back and looks inside. What we have here is a power supply, high voltage power supply, DC power supply. No, DC plus AC. There is a little bit of AC over here. You have 3 voltages that we're going to use. This is called the filament bias supply, filament supply. This is actually turns out to be AC right here. And it's about 4, 5, 6 volts. And then we have this accelerating voltage, which will go up to 500, 600 volts over here. As you can see, there are always 2 electrodes, one positive and one negative. Positive one being the red and the negative one is black. Not for this, for AC it doesn't matter really. And then we have here is the supply for the deflection voltage on the y-axis that we're going to do. So if you are in the lab, just connecting these connectors to the proper one is a chore actually by itself. So the deflection voltages go over here, the accelerating voltages go on this side of the apparatus, and as you can see that it goes in over here, the anode, this is the positive, and the cathode is negative over here, and then the filament supply is from there to there. All right, and what happens here is that all the current actually goes to the back of the CRT tube. That's basically the back, and it actually goes to its proper position, and we have actually has an open tube right here. So it's all the bias voltages are applied here, and the current goes into this over here. There's a metallic part where when you put current into the metal, it actually emits electrons. And then you have a very high voltage, 500, 600 volts, which will attract the electrons through these through that length actually. And then when it comes out here, you put a bias voltage here, and then the electrons can either go up or go down, and you can put another bias voltage here in the X, and then it go on the side. So one is going up and down, the other one is side to side, X and Y. And that was what in your CRT tubes, if you're using an old television monitor or a computer monitor, it's a bulky computer monitor, that's what is behind actually, and there are bias voltages which actually controls both the X and Y direction. So there are a couple of things I would need from here, and I'll show you later on. I have to measure something, and I will put that on the board. Remember that the distance between the deflecting voltage electrodes right here, I have to measure that, and that's the X, delta X direction. I have to measure that for you. So for the time being, what I want to do is I'm going to turn this on, and I don't know whether you can see the voltage. Can we see the voltage up here? Oh, here, if we don't. So what I'm going to do, I'm going to put this like that. Maybe you can see it now. It's see now. So, and so I started it on. There's already filament voltages present. I just want to make sure that I get that. So I put it on 20, but with the AC voltage, okay. And let me see if I can get any any voltage here. So that's okay. Let's see. Am I doing? This is on. That's. Oops. Sorry. Let me just check 1 second. I should be getting some voltages up here. So that's this is an AC voltage. This is sometimes difficult to get the proper voltage here, but I know that this is working already. So this would be on the order of 6 volts or so, but let me get this somewhere else and measure it. Give me just a second. If I don't get this one, it's not end of the world. It's because it's very difficult to measure actually this AC voltage over here. But I know that it's working because I can get an electron spot. I don't want to measure the voltages over here. This is a very high voltage, and you're going to get this right here. And you will see if I increase the voltage, it will gradually get a green spot over here, hopefully. I'm going to go to very high voltages, and the green spot is already appearing at 300 volts. If I increase it to 600 volts, so that's 600 volts, and you can see that green spot. There is a focusing material which actually uses X and Y component, and you can see that it gets smeared out, and then it can get a point right here. So that's all I need. I don't need to even center it. And then I'm going to only use one of the deflecting voltages, and I have that connected here. It says X deflecting voltage. Whether I can use X or Y doesn't matter. Let me use Y, which is the one behind. But then I have a problem with the Y deflecting voltage. This is only because of the way this is constructed. So let me just go back to X. This is fine. And then all I'm going to do is move this knob to the right, and it will give me the voltage for this setting. And you can see when I move this voltage will continue to go up, and this part is going to move from its central position. Because it's, when you have the voltage, there's an electric field, electric charge, electron charge minus the electric field, there's a force applied, and in this case the force, it goes over down here. So what I'm going to do is I'm going to move it only up to here, and I'm going to measure how much distance I actually moved it. So this is about 1.5 centimeters. So my delta y, in this case delta x, which is same as delta y, will be 1.5 centimeter. I wrote this down. There are a couple of other things I need to write down. That's the entire experiment, by the way. But the main thing was actually to use this stuff. That's my accelerating voltage, V2, which is about 37 volts. It's okay, 37 is good enough. And then my accelerating voltage was 601 volts. Okay, there are two more things I need to give you to do this experiment. I need to give you that D, and that D would be just the distance between these two electrodes, and it's literally 4 millimeter. So D is 4 millimeter. And then other things I need to give you is a delta X, basically the anode. This is the distance that the electron actually travels through. So that distance would be on the order of, this is 4 centimeter, 4.3 centimeter. So delta X is 4.3 centimeter. That's basically where the bias voltages are applied and the electron is accelerated through that distance. So again, tomorrow, actually, that's when I'm going to record this, the next lab. Even though for you, it will be much later because we haven't gone into the magnetism chapter yet. We're going to apply a magnetic field and bring this spot back into the center so that the electric field force and the magnetic field force equals, and we can find E over M ratio from that. So for this, we are already done because all we need was accelerating voltage, then the deflecting voltage, and also that's the filament voltage, and then we need those numbers. So main thing was that also we used a high voltage power supply. So let me go to the board and write this down for you. That will help you in your calculation. So my V1, this is the accelerating voltage. Is 601 volts. V2, this is the deflecting voltage, and that's 37 volts. I have moved it, this delta Y, I have moved it by 1.5 centimeter. Okay, you can actually convert that into meter if you want. And then the D distance was 4 millimeter. This D distance you want to, this is actually V2 over D. That's what we need at that electric field. And then delta X is 4.3 centimeter. This is the distance that the electron travels. Okay, so that's 4.3 centimeter. All right. So let me just think about this one more thing. Actually, if I am looking at the horizontal distance covered by the electron during this time, it's not 4.3. I'm only looking at between the accelerating electrodes. Actually, it's not 4.3. It's actually 8 centimeter. My apologies. Actually, it's 8 centimeter. This is the time the electron exists before it actually hits the screen. Let me check one more time. Because we don't have any documentation for it, and we need to figure this out, what the centimeter I really need. It's actually much larger than that, what I thought. It's actually on the order of, because it accelerates during, this is the time it accelerates. I need only the time through which accelerates. And if I go back, give me 1 second because I don't want to confuse you. Delta X Vx times T. So this one would be on the order of not even 8 centimeter. It would be a little bit larger than that. I have to, sorry. This is actually on the order of 12 centimeter. Sorry about that. Because the 4 centimeter originally I thought was just between the electrodes, but that's not what I want. I want the entire segment. Let's work on this, and I will talk to you in the class, and we'll compare our notes and see what we get from there. Okay? Thank you. See you in class.